All right, let's take a look at 10.1 confidence intervals. Um, we're going to start out in this section just kind of as an overall introduction into what we're getting into here. And then we'll have two more or a few more sections on the actual computations to get from scratch a confidence interval. So, first, we're going to talk about what it is, and then we're going to get a feel all around for its usefulness and how to kind of deal with it. Okay, so we're going to talk about point estimates, which is our starting spot, and then our error, which helps us get our confidence interval. Um, then we're going to go ahead and calculate, given an interval, we're going to calculate a margin of error and a point estimate, a starting spot. And then we're going to connect it to the empirical rule. So, in inferential statistics, we use sample data to make generalizations about an unknown population. The sample data helps us to make an estimate of a population parameter. So if you go back to the beginning of the semester, chapter 1, chapter 2, when we were really looking at like statistics in its introduction, we talked a lot about how we don't like populations. Populations are big and bulky and inefficient. What we like is samples. And we can collect samples on anything, and they're efficient, and we can always calculate things with a sample. We can always get those statistics. And then what we do is we take those statistics and we say, so from a sample, these statistics tell us this. Like the mean, the middle tells us this, or the standard deviation, the spread is this. From a sample, then we use those things to say, so we think the population's mean and standard deviation would be these values. Okay? Basically, we're using a sample to kind of diagnose some statistics, and then we use that result to say we think the real population looks like this. So it says, suppose you were trying to determine the mean rent of a two-bedroom apartment in your city. You might look in the newspaper or on the internet, write down several rent prices, and then find the average. This is called the point estimate for the true mean. So you're starting with the sample, just several rent prices. You add them up, divide them to find the mean. This is called a point estimate. This is our starting spot for our confidence interval. We can do the same with proportions as well. So this was for mean. We can do the same with proportions. If you are trying to determine the percent of times you make a shot when shooting a basketball, you could count the number of shots you make and divide by the total number of shots you took. This is called a point estimate for a true proportion. All right, so in both of these, for the mean and the proportion, we're going to take real data, a sample, add them up, divide them, do whatever mathematical manipulation we got to do to find that point estimate, that starting spot, where we can say from this sample, we know this. We know the mean rent is this, or we know the proportion of shots made is this. We will then infer that the true population is going to be in some interval. That's what we're going for. These point estimates are just our starting spot. So the sample mean x bar is the point estimate for the population mean, mu. The sample proportion p prime is the point estimate for the population proportion p. Each of these point estimates are statistics because they are data about the sample. We realize that the point estimate is usually not the exact value of the population parameter, but it is very close to it, and we can use it to make inferences about the population. So basically the idea is, if I take a sample and I get an average of 45, well, I'm going to learn that there's some manipulations that some mathematical computations we're going to do that tell me I can get an interval where I take 45 minus some amount and 45 plus some amount, and I get this interval, this range. Okay, it's an interval, but it's like a range where I say, hey, I know from the sample 45 is the mean, but for the population it's going to be between these two values. All right, that's what we're going for. We can't actually find the population mean because it's too bulky and burdensome. but we can find the mean from a sample and then go ahead and infer a range. Okay? What do we add and subtract? Well, we're going to add and subtract what's called the error. Okay? We're going to add and subtract the error to get that interval, to get that range of the true population, either mean or proportion. All right? So we're going to, and now when you hear that word error and you think about these intervals, you probably have seen something like this before in like presidential polling or political polling. When we look at polls, we see things like one candidate might get 42%, and then in very fine print, they say that there's this error down below of plus or minus 3%. And what that implies is really, in our sample, we got 42% for that candidate. Out of all the people we asked in our sample, 42% said they would vote for that candidate. But we don't know what the true election result's going to be. So we think, through math, very confidently, we think that if we take 42 minus 3 and 42 plus 3, then the real outcome will be somewhere between 39 and 45% of the vote. Okay? The real outcome of that vote, whenever they vote, would actually be somewhere between 39 and 45. Now, if you watch the news and they talk about these polls, they almost never mention that margin of error, okay? They usually just stick to the sample results. And in 2016, that was a big deal because all the polls came out and had Hillary Clinton, in the presidential election, had Hillary Clinton beating Trump. It was somewhere around 45 to 42 going into the day of the election. This is what the polls were showing. So for Clinton and then for Trump. But there always was this little margin of error down in the fine print down below of plus or minus 3.5 or close to that, okay? And so the reality is people got upset because, oh, statistics, polls, they're worthless. They're worthless. Trump won. None of the polls showed that Trump would win. Well, it actually does show that Trump would win. 45 minus 3.5 takes us all the way down to 41.5, and then could be all the way up to 48.5 for Clinton. And Trump was somewhere around 38.5 all the way up to 45.5. That's really what these polls show. There's this actual true population range, this confidence interval based on the error and based on the point estimate, the starting spot. And so you can see there's a lot of opportunity here for Trump in reality from this poll to win. Now, what actually happened was the actual results of the general election actually came in something like 45 to 43. Okay, Clinton in the popular vote, Clinton did win 45 to 43 or so. All right, but Trump won the electoral college. All right, because of how we choose a winner. So I know people will want to say, oh, don't trust the polls, don't trust the polls. The polls are spot on. We didn't interpret it like we should. Okay, so now you know. Be wary of those polls. Understand them. Don't take them for face value. Okay, don't let somebody else tell you what they mean. Understand that Clinton should have been somewhere between 41 and 48, and she was. Trump should have been between 38.5 and 45.5, and he was. So the polls worked, okay? And here we see a confidence interval is just another type of estimate, but instead of being just one number, it is an interval. The interval of numbers is a range of values calculated from a given set of sample data. Confidence intervals for unknown population parameters like mean or proportion. We take our point estimate minus some error and our point estimate plus some error. All right? The margin of error determines the width of the confidence interval. The margin of error depends on the desired confidence level. So, this confidence level is one piece of information that we actually get to I don't know if the word we can kind of inject into our results. Okay, This is what we can control as our confidence level, or percentage of confidence, and the standard error of the sampling distribution. We will learn in a later section how the margin of error is determined. The confidence interval is centered on the point estimate and is likely to include the unknown population parameter. It is important to keep in mind that the confidence interval is a random variable, and it is the population parameter that is fixed. So I want you, especially in this section, to think in terms of a number line where we have some kind of point estimate in the middle. And then we add the error to get to some idea, some number over here in our interval, and we subtract the error to get to some piece of information over here. Okay? So that point estimate can either be the sample mean or it can be P prime, the sample proportion. Okay? But we're going to add some error, we're going to subtract some error. And this picture will help us through the rest of this section, because in the rest of the section they're going to give us things like, hey, the lower bound was 42 and the upper bound was 48. What is the error and what is the sample mean? Okay? So if I just gave you a confidence interval of 42 to 48 and I said, what's the point estimate and what's the error? Well, what would we do to find the middle here? Well, what we would do is should make sense. We need to find the distance from 48 to 42 and then cut it in half, because this error number and this error number are the same. We have two pieces, okay, centered at the middle that go from this extreme to this extreme. It makes sense that we would take 48 minus 42 and get 6. 6 is the overall spread, right? From 42 to 48, the spread is 6. So that means the error must be half that. So the error must be 3. So we subtract 3 and we add 3. Well, what did we subtract 3 and add 3 from? Well, it makes sense we could take 42 plus 3 to get to the middle, 45. Or we could take 48 minus 3 to get to 45. See how if we're given an interval and we draw this kind of time, or this line graph here, and we list our minimum and our maximum, understanding that our middle's here. If we find the distance between the two through subtraction and cut it in half, that gives us our error. And then once we have the error, we can either add it to our minimum value or subtract it from our maximum value to find our middle. All right, that's how this works. 45 minus 3 is 42. 45 plus 3 is 48. 45 is our point estimate, whether it's our mean. It can't be a proportion because a proportion has to be a decimal, right? So this would be a good example of a mean of 45, confidence interval of 42 to 48, because the error is 3, plus and minus 3. All right, so a random sample of registered attendees were surveyed and asked if they learned anything new at the seminar they just attended. The proportion of those surveyed who answered yes on the survey is 0.52, with a margin of error of 0.04. So we have a starting point. A P prime is 0.52. Why do I know it's a P prime? Because it says it's the proportion. Is 0.52, and then we have this error of 0.04. So if we wanted to construct a confidence interval, it makes sense that we're going to take our point estimate, 0.52, and subtract the error. We're going to take our point estimate of 0.52 and add our error, and that gives us 0.48 on the low end. And so 0.52 minus 0.04 is 0.48, and then if we add them, we get 0.56. So there's our confidence interval, our confidence interval for what the true population might show. Okay, all we know is that the sample showed us 0.52. The population is going to be somewhere between 0.48 and 0.56. Okay. Here is two pieces they put out there. Feel free to write them down, but I feel like I've already walked through why these two work. Okay, if we know the point estimate, subtract the point estimate from the upper value of the confidence interval to find the margin of error. And then if we do not know the point estimate, subtract the lower from the upper, and then divide by 2. We've already done both of these things, and that number line really helped us see why these two rules would help. Okay? So I'm not going to really reference these two rules very much. I'm going to reference that number line. So it says, question, suppose we know that a confidence interval for the mean height in inches is 54.2 to 56.5. It wants to know the margin of error. Well, I'm going to go ahead and put on my number line 54.2 and 56.5. And I know that some point estimate is in the middle. This happens to be a mean that I'm going to find. All right? So it makes sense that I want to find the distance between the two. So I'm going to get my calculator out. I'm going to take the biggest minus the smallest, 56.5 minus 54.2, and we get a spread of 2.3. So 2.3 from here to here, okay? But I know that I start in some middle spot and I subtract the error and I add the error. So that means this spread of 2.3 is a distance of one error and one error. That's two errors. So I have to divide it by 2. And we get an error of 1.15. Could we find the middle number here, the mean? Sure. We were just asked to find the margin of error, so that's good. We did that. But if I wanted to find the mean, I could go ahead and take 54.2 plus 1.15, and it would be 55.35. All right? So as you do these problems, sure, you can, if you can digest these two rules and refer to them, go ahead. But I just prefer to use this number line where I have the point estimate in the middle. I know I'm subtracting an error to get to my lesser value. I'm adding an error to get to my upper value. And then it just becomes what looks more like some decent middle school math rather than some rules that who knows where these rules came from if I didn't explain them to you, right? Well, now you know where these two rules came from, why they work. Okay? Suppose we know that a confidence interval for a population is 0.33 to 0.41. Find the margin of error. So again, I'm going to draw a number line. 0.33 on the low side, 0.41 on the high side. And I know this is going to be a proportion, so it's a p prime, right? It's not a mean, it's a proportion. I know I would subtract an error and I would add an error. So from here to here, it's 2 errors. So if I can find that distance by subtracting, I'm going to take 0.41 minus 0.33, and I get 0.08 is the overall distance, but I want to know what one error is, not both. So I'm going to divide by 2, and I get an error of 0.04. If I wanted to find the middle number, well, I could just take the lower number, 0.33, and add 0.04, and my p prime, my point estimate, is 0.37. What would a problem like this look like? Well, we can go right back to the polling. 37% of people from sample said this. We had an error of 0.04 or 4%. We get an interval, confidence interval of 33% to 41% for the true population proportion. All right, so I don't think we need to go through those anymore. Let's just go ahead and show how this works for the empirical rule. Understand that one standard deviation was 68% of the data surrounding the middle, surrounding that mean, the best point estimate. So one standard deviation below and above was 68% of the data. 2 standard deviations was 95%, and 3 is 99.7%. How does that work here? Well, we can apply the empirical rule to the sampling distribution for the sample mean or the sample proportion to determine a confidence interval. Using that central limit theorem that we looked at last chapter, the sample mean follows an approximately normal distribution with the same rules as the central limit theorem, where n is the sample size and the standard deviation is presumed known. Applying the empirical rule, we can say that 99.7% confident that a true population mean lies within 3 standard deviations. Meaning if we take our point estimate, our mean, subtract 3 standard deviations, and then we do it, take the point estimate and add 3 standard deviations, we can say that we are 99.7% confident. Generally, if z is the z-score corresponding to the desired confidence level, the confidence interval is shown as follows. Don't get too far into this. You're going to see that the next sections, when we actually create confidence intervals from given statistics, this empirical rule is kind of a bridge to get there, because we're going to start answering 95% confidence, 90% confidence, 99% confidence. And this empirical rule kind of is the bridge to get there, because we already know rules about 1 standard deviation, 2 standard deviations, 3 standard deviations. Well, remember, these number of standard deviations is also a z-score. So this is a z-score of 1, 2, and 3. Well, what if we get a z-score of 2.5? It's going to be somewhere around here, and we're going to be in some kind of confidence level of like between 95 and 99, right? That's the idea that we're going to see moving forward. The confidence level is the one thing we do get to determine, and we'll talk more about that moving forward. But this empirical rule is just kind of the bridge to get us to where we're going. How do we create these confidence intervals, and how does confidence level address, make its way into there? All right. Let this sink in. Watch it as many times as you need to. Go back through it, pause it, play it. Let me know if you have any questions.